part C, we're looking to find the total distance traveled by the diver's shoulder from the time she leaps from the platform until the time her shoulders enter the water. And so what we're looking for here is the total distance traveled on the parametric path. We could also call this the length of a parametric curve. And that's going to be the integral of the square root of dx dt quantity squared plus dy dt quantity squared. That's not the second derivative, it's just the square of the first derivative of dx dt and dy dt. And so what we want to do then is to integrate this from 0 to a, which we found in part B. And so for this we're going to recall our calculator. I'm going to go back to y equals, and we'll leave both the things that we have in there alone. We'll turn off equation number 2, and we'll put each of the individual equations. Well, we already have, I believe that's dy dt in there, and so we can get started with this. Dx dt is just 0.8, so it's okay that we don't put that in there. So we're going to do 0.8 to the second power. That's dx dt quantity squared. And then we're going to add to that y1 quantity squared. So that's vars, y vars, function y1 squared. And that should do it. So all we need is square root of dx dt quantity squared plus dy dt quantity squared. We're going to integrate that from 0 to a, where a is a value 1.936 seconds that we've already stored in the alpha a. So I'm going to go to Zoom Standard, and I'm ready to integrate from 0 to a, and the value is 12.946, and that would be in meters. And so we're done with part C as well. In part D, we're asked to find the angle theta, where theta is between 0 and pi over 2, between the path of the diver and the water at the instant that the diver's shoulders enter the water. So what we're actually looking for here is the slope of the tangent line of the parametric curve at that particular instant that the diver's shoulders enter the water. And since we have the tangent of that, then we're going to use arctangent to find the angle associated with that tangent. And so if you recall, the slope of the tangent to the curve on a parametric curve is dy dx, which is dy dt over dx dt. And we're looking to evaluate this at 1.936 seconds. And once again, I can go back to my calculator. I'm just looking for dy dt, which is y1, over dx dt, which is just 0.8. So I'm going to create a new function, first turning off all the other ones. So I want dy dt, which is y1, vars, y vars, function y1, then divided by 0.8, which is x. So I'm looking for the value of dy dt over dx dt when t is equal to 1.936. So I'm going to go ahead and zoom standard, and I'm looking for the value of that curve when t is equal to a. So I'm going to do second value and type in a, and I get for that a negative 19.21913. And recalling that x here is actually my t, and y here is actually my dy dt over dx dt. So it's negative 19.219. I can store that in b. It's currently in the y variable. Actually, getting to store that when it's a y variable is not too easy. So I'm going to write it down with some extra digits and then find the arctan of that. And that comes out to be negative 1.5.